Hey guys, Greg here. Today let's talk about a very popular algorithm known as dynamic programming. Now, dynamic programming generally has 4 different steps. The first thing that you would do is generally don't use dynamic programming at all, and you would generally write what is called the naive recursive solution. Now, this might have a very big runtime. This might be something like big O of 2 to the n, or maybe 3 to the n, or maybe something like n factorial. So that might be really slow, but that's okay because it's really easy to optimize that with the top-down DP technique, and this is known as memoization, and it basically just means using a cache or remembering function values. Now, this is still using recursion, although you're basically just applying a cache to that. The third step is generally to switch the top-down technique to what is known as a bottom-up technique. So this is bottom-up dynamic programming, and generally we call that tabulation. And tabulation is a bit of an old-timesy word. Generally, we just mean table or filling out an array, and we would do that with loops. So bottom up uses loops and top down uses recursion. They generally have the same runtime, except bottom up dynamic programming is generally faster just because most programming languages are better at doing loops. Okay, and then 4 is kind of like an if possible thing here. The last step would be if possible, you would do bottom up dynamic programming but get rid of the space. So you would do a constant space solution, which basically means instead of filling up that array, you do a clever thing with variables so that you don't have to fill up an array. Okay, so those are the 4 ideas, and then to learn about dynamic programming, we will solve the Fibonacci problem where we will describe this in complete detail. Let's solve Fibonacci number, LeetCode number 509. So the Fibonacci numbers, commonly denoted as f of n, they form a sequence called the Fibonacci sequence, such that each number is the sum of the 2 preceding ones, and we're starting at 0 and 1. So that is the sequence defined by f of 0 is 0, f of 1 is 1, and more generally for anything that's not 0 and 1, only positive numbers, so things greater than 1, f of n is f of n minus 1 plus f of n minus 2. Okay, so if n is equal to 2, then the output would be 1, because f of 2 is defined as f of 1 plus f of 0, and these are just base cases, so f of 1 is 1, and f of 0 is 0, and so 1 plus 0 is just going to be 1. So the total answer there would be 1. And if n is equal to 3, then the answer would be 2, because f of 3 is f of 2 plus f of 1, and f of 2, we just calculated that above, that's going to be 1. f of 1 is also 1, and so f of 3 is equal to 2. So the first step of dynamic programming is usually writing the recursive solution, aka not using any dynamic programming at all. So to do this, it's actually really easy. We basically just define the function that says exactly what we've been told here. And so basically if n is equal to 0, then we know our result is 0. If n is equal to 1, then we know our result is 1. Otherwise, n is going to be greater than 1. And so we have to return, you actually have to write self here because LeetCode puts it in a class. You have to do self.fib on n minus 2 plus self.fib on n minus 1. If you run that, this is definitely going to work. And actually, because it's an easy here, you are going to submit it and see that it's accepted. However, you can definitely see the time here, and clearly we can make some optimizations here. Okay, so let's come back to this in a moment. I'm going to explain the top-down memoization approach. Let's think about what our current code is doing on the function call of f of 6. So say we wanted to know what f of 6 was. Well, f at 6 is the sum of f at 5 and f at 4. It is going to be the sum of those 2 values. But these are function calls, and so f of 5, that actually is going to need f at 4. And f at 5 will also need f at 3. Over here, f at 4, that will require f at 3. This will require f at 2. Okay, very important to see here that f at 4 is showing up multiple times, okay? We have multiple different calls of this function, same as f at 3, that's going to show up in multiple places as well. It's actually going to show up over here as well, because f at 4 requires f at 3 and f at 2. And this is what we call overlapping subproblems, because we're computing the same function call in multiple different parts of the code, and that's something you don't want to do, and we're going to be able to apply dynamic programming to optimize that, so we can avoid that. Okay, so this would be our complete tree of function calls here. So it's always going to end in either f of 1 or f of 0 because those are the base cases, and we kind of need to start from there before we can do anything. Because if we're trying to find f of 6, well then that's, for example, going to need f of 5, which will need f of 4, which will need 3, which will need 2, and from 2 we can actually start to get some stuff done. Because 2 says, okay, it needs f of 1, well that's going to be replaced with its result, which is 1, and it also needs f of 0, which is going to be 0. F of 2 can actually say that it's 1 plus 0, and so that will be replaced with 1. F of 3 now needs f of 1 as well, and f of 3 will be replaced by its value of 2. F of 4 needs f of 2, f of 1 is 1, and f of 0 is 0. So we know again, we computed again that f of 2 is 1 plus 0. Note that we really shouldn't be computing it again. We should kind of just be remembering what the result of that function call is. We'll be doing that in a moment. Okay, so I'm not going to kind of compute this whole thing here and show you how that would bubble up because that'd be kind of nasty. But essentially to compute f of 6 here, it's first going to worry about the left side here. It's going to try and get f of 5. And so this would do kind of compute all this stuff to get f of 4. And then it would do all this stuff to get f of 3. That way f of 5 could be replaced with its result. And f of 6 would also need f of 4. And so that's going to be the sum of this branch plus the sum of this branch. F of 4 would be replaced by that number. And f of 6 would be the sum of f of 5 and f of 4. All right, let's make one very important observation about this tree here. There's essentially one thing right here, f of 6. Over at this level, there's 2. At this level, there's 4. At this level, there's 8. At this level, there could be at most 16, but actually some of these things didn't need to get any further. So, there's at most 16 here. There'd be at most 32 over here. And so as you can see here, it's doubling. This essentially is, we'd have 2 to the 0 here. These are equal. 2 to the 0 is 1. 2 is equal to 2 to the 1, 4 is equal to 2 to the 2. You see where I'm going with this, okay? So it's powers of 2, and essentially we're doubling. And so at every single step here, basically if you have 6 and you're going all the way down to 0, that's n plus 1 things, or roughly n things. Essentially, every single time we have one more number, so 6, 7, 8, we are doubling. We're getting a doubling effect. That essentially tells you that our code is going to be roughly a big O of 2 to the n, okay? There's going to be roughly 2 to the n things that we have to do. And we're going to see how to optimize it now via what we're going to call top down, because I'll explain that in a moment, but we're basically starting at the top here and we are working our way down the tree. Top down dynamic programming via something called memoization. Okay, top down DP and memoization, they're essentially synonymous. Now you might have been told that dynamic programming is hard. I know that I was kind of scared of it for a very long time, but it turns out that top down memoization is really, really easy. It's actually almost common sense. It basically just says that, hey, if you've computed a function call like f at 4 before, you don't actually want to do the whole tree stuff. Because like right now, if you want to know what f at 4 is, well, we'd have to do all of this stuff. And so if you actually do that multiple times, you see f at 4 and you do all this stuff. And then over here, you see f at 4 again. You just don't want to do all this stuff again. You want to do an O of 1 or constant operation. F at 4 is just a number we've already computed. Call it x. If we figured out the value of x, well, we just want to remember what that is. And so generally you would use a dictionary, which starts with your base cases because we know our base cases. It's going to map the function call. So f of 0, it's essentially saying f of 0. We're going to say f of 0 is a value of 0. F of 1 is a value of 1. And we usually implement this as a hash map, or in Python, a dictionary. But in general, the kind of general term for this is just a cache. It's caching things. It's remembering things. And yet another term for it, generally what we'd call it in dynamic programming code. So the variable name you'd probably call this is memo. There's so many different terms here: memo, cache, dictionary, hash map. They're all just saying map a key to its value, aka the function call to that function call's result. So we do a top-down approach, top-down because essentially you would try to calculate f at 6, but we know to do that, we're actually going to need to go all the way down to our base cases first, because we're going to need f at 2, which needs these base cases, okay? So f at 2 is f at 1 plus f at 0. We know those things because they are both in the memo, and we'd replace f at 2 with its function result, which is 1. But right before we do that, before we actually kind of return over here to this guy that our our result is 1, what we would do is we'd say, okay, f at 2 is 1. Memorize that. We computed that. Now, whenever we see f at 2 here, you can actually just kind of remove these from the branch because we can do this right now. It's never going to need these things because we're just going to calculate from the hash map what that value is. And so we don't need those other function calls. Okay, so f at 3 also needs f at 1. That's in our memo here. The result is 1. And so this gets replaced with 1. F of 3 ultimately gets replaced with 2. And so f at 3 is replaced by 2. Remember that for later. So now we basically don't need these function calls anymore because f at 3, we know that as a number. F at 4 is going to be replaced by 2 plus f of 2, which is 1. And so f at 4 is going to be replaced by 3. F at 4 is 3. We can remember that. And so that means we also wouldn't need to compute those. See what we're doing here? We're getting rid of basically the whole half of the tree here. We really only need to go the depth of the tree because we're just working our way up now. By the time we kind of go from the left all the way up here, we're essentially done. And that's why this is so fast. So f at 3 is going to be replaced by 2, and f at 5 is going to be 5. We can remember that, although it's not actually going to come up at all. And finally, f at 4 is going to be replaced by 3 so that f of 6 is remembered as 8. We would actually kind of put that finally in the dictionary because that's the thing we ultimately wanted. We asked what f of 6 was, and so we kind of could just return the memo at 6, which is going to be that value right there. So this is top-down dynamic programming via memoization. We're using this cache or a dictionary to, when we compute a function call, we're going to remember what that is, and that is going to make this, as you saw, a big O of n calculation. Why is that? Well, essentially what we did is we figured out our base cases at the beginning, then we figured out the next value, then the next value, then the next, then the next, then the next. And we're figuring those up basically from 0. That way, by the time you get back up to the top here, there's really not a whole lot of work to do. You don't have to do all this repeated work. Okay, so let's code up this approach. Now it's going to look a little bit different, although functionally it is very, very similar. We need a memo, which is going to be a dictionary, and it generally starts with our base cases. So we say that f of 0 is 0 and f of 1 is 1. Now that we have this, we can have a helper function, which I'll just call f of x. Now, if x is in the memo, okay, so if x is a key in our memo, that means that we already know the result of this function call. So we simply just return memo at x. However, if we don't know, then this is our first time computing it. We want to set memo at x equal to what it should be, which is f at x minus 1 plus f at x minus 2. And so we simply, at this point, just return memo at x. Now we need to tell LeetCode what fib at n is, and so we can do that. It's just return f at n. It needs to compute all of these up and make that whole dictionary of all of the stuff, including f at n, and eventually return us that result. So if you run that, that is going to work as well. And as you can see, it's actually quite fast. It's so much faster than our other one because this is going to have a time complexity of big O of n, and the space complexity, well, we actually didn't talk about that, but if you've done backtracking or DFS before, the height of the recursive call stack is actually n deep. And so the space complexity, because of the recursive call stack, is actually going to take up O of n space as well. Okay, so now let's do bottom-up dynamic programming. And the reason it's generally preferred is because it eliminates recursion, and programming languages usually aren't very good at recursion. Now, bottom-up is actually way easier than you might think for this problem. Sometimes it can be hard to come to, but this problem is actually really obvious. If you have the sequence of 0, f of 0 is 0, f of 1 is 1, f of 2 is the sum of the previous 2, which is 1, f of 3 is the sum of the previous 2, which is 2. F at 4 is the sum of the previous 2, which is 3. 5 would be 5. 6 would be 8. You see where we're headed? Well, basically what we're doing here is if you want to know the next number, that's just the sum of the previous 2 numbers. And so that's really not too bad. Now, it's easy to kind of forget about this idea when you get lost in the wording of the problem, but you should definitely keep this in mind. Now, generically, this is going to be called tabulation. Okay, we're basically just creating this table here. This thing is a table because basically it's an array. You can see these are basically indices where these are f of that value, and this is the result of f at that value. And it's bottom up because we're basically saying, okay, let's not even worry about like f at n right now. Maybe n is equal to 8 in this case. Let's actually just start at the bottom, so at 0, and let's work our way up. So bottom up, that's why it's called that. And often called tabulation because you generate a table in the process, and you don't use recursion to do that. You would use like a for loop. Okay, so this really is the approach. There's really not a whole lot to say here. If you wanted n is equal to 8, now there's multiple ways to do this, but the most efficient approach would basically be to create a really big array at the beginning and just fill it with a bunch of zeros, because we know we're going to end up filling this table, and you can avoid kind of using the append operator, which kind of just dynamically increases the array as you go, by just creating all of this up front. So you would do this, and actually if n is 8, then you would create basically n plus 1 slots here because the sequence actually starts at 0. So you'd initialize this to be empty, and very important, you would want to initialize your base cases in the array, because this isn't going to work unless you set this to be its base case of 1 and f of 0 just happened to be 0. But in other problems, you might have to set that to what its actual result is. Now, essentially what you would do here is just kind of loop through these indices, because f of 2 needs to get computed into this slot right here, and it's revolving these two values. Okay, it's basically just saying that the dp, so generally you would call this array dp just for fun, you would be setting dp at I, so if I is 2 here, you would set that equal to dp at I minus 2 plus dp at I minus 1. Okay, that's just a fancy way of saying this is going to be the sum of the previous two values. So we would set this to be 1, and we would kind of just move this along here. So then I is 3. You would set the array to be these two values, which is going to be 2. You'd set the dp at 4 to be dp at 3 plus dp at 2, and so this is going to be 3. And you'd basically just do exactly what we were doing, which is the sum of the previous two values. You would get all the way up until the value that you're interested in. You would compute that one, and then you could just return basically the final number in the array, or equivalently in this case, that's going to be returning dp at n. So as you can see here, we're basically just going through a for loop of n numbers, and so that's going to be a big O of n approach, and we're also taking up O of n space because we're kind of storing all this stuff in the table. So it's still going to be a time complexity of O of n and a space complexity of O of n as well, but this is generally preferred over top down because it avoids recursion. It uses for loops, which programming languages are just generally better at. So let's code this one up. Now for this, you don't always have to do this, but it can generally be useful just to have your base cases. If n is equal to 0, you can return 0. If n is equal to 1, we can return 1. And that just kind of safeguards your array out of bounds issues. So what we want is we're going to get an array called dp, which we'll set to be an array of n plus 1 zeros. Okay, so you do it like this. That makes it so that f of 0 is in the first slot, f of 1 is in the second slot, and this is going to make the last index of the array f of n, and so that's why we have n plus 1 things. Okay, you set your base cases. This is a little redundant, but dp at 0 is going to be 0, and dp at 1 is equal to 1, and then you just kind of loop through the indices that you need. We go for I in the range of 2 until n plus 1. Why is that? Well, the first index of interest is f of 2, and we want to go up until f at n, and so this is exclusive. It's actually going up until n, and we can keep setting dp at I equal to dp at I minus 2 plus dp at I minus 1. That really does all the work for us. It's going to start from the bottom and generate that table all the way up until the very last value, which is dp at n. And so you can just return dp at n. That will work, and that's exactly what is one of the best solutions out there. I'll show you something slightly better, because this has a time complexity of big O of n, and it has a space complexity of big O of n. It turns out there's a slight optimization to this approach, which I will visualize now. Basically, you would just count this up, because if you have 0 and 1 are your base cases, well, the next value would be the sum of the previous two, which is 1. The next one would be 2. The next one would be 3. But hey, this is keeping these numbers in memory. We don't need to do that. You start with 0 and 1. Your next value would be 1. 1. We actually don't need this value, so let's remove that. We have 1 plus 1, which is going to be 2. We don't need this one. The next value would be 3. We don't need this one. The next value would be 5. You see what we're doing here? So it was easy to convert the top-down approach to its memoization approach, because you basically just apply a cache to it. Here, in this case, we really just turned this approach into a variable constant space approach. And so you would still have your base cases. We'll call this one prev, and we'll call this one cur, but we don't need our array. We can keep the same stuff here most of the time because you're still going to do the same stuff. But what you can do here, and it's actually quite clever in Python, you can set prev and cur simultaneously to be cur and prev plus cur. At the same time, it updates prev to be cur and cur to be prev plus cur. This essentially always keeps cur as the new number, which is the sum of the previous two, and it also always keeps prev as the one behind. And at the end of this, you would just return cur, because that's kind of your end result here. This would give a time complexity still of O of n, but it drops the space complexity down to O of 1. We can see here that this is also going to pass the test cases. This is probably the best solution that you would come up in an interview. I'm going to annoy you by saying there is one last thing. Technically, for Fibonacci, there is actually a log solution, which involves the golden ratio. It's essentially a mathematical calculation, and raising this to the power of n is going to take log n time. If you run this, this is actually going to work, and it will be the fastest approach, but it's really just silly. So I hope you learned a lot about dynamic programming, and I hope this was helpful, guys. Drop a like if it was, and have a great day. Bye-bye.